Okay, so our first exam is next week. Like I explained, on the first day, we have kind of a unique way of doing the exam. So on Monday, we will have an in-class written exam. Okay, so on that part of the exam, you will, for this test, you'll be given spectra, you'll have to identify peaks, draw structures, and after our next chapter, which we'll do the next couple of days on radical chemistry, we will have some reactions to do and mechanisms and things like this. So this will be the written exam in class. We will split between two different rooms, and by tomorrow I will post a room assignment. And so what I try to do is over the semester, everybody will have a time to take exams in here and then elsewhere as well. Okay, and so I would ask you that when I post those room assignments, make sure that you go to the room that you're assigned to, because otherwise we could end up with not having enough exams in one of the rooms, right? And that's kind of a bad situation. Starting after our exam, class exam on Monday, so at 11:30 on Monday through Wednesday at 8:30 when the testing center closes, you will be able to go in and take the computer portion of the exam. So that exam has been set up, so go ahead and reserve a time slot to go in and use the testing center. You'll have 1 hour to do 25 multiple choice or computer-based, not all multiple choice. There'll be multiple answer and some fill-in and things like that, questions. Once that's closed on Wednesday, you will have between Wednesday night and Friday night to redo the computer portion of the exam. And what will happen is that an identical copy of that written portion will open up on Canvas. And you can go into that exam, work on it, go back out, come back in as many times as you want during that time period until you actually submit the exam. And then once you've done that, you're done. Okay? So that's the format. Like I said, we're going to be finishing up chapter 14 today, and then chapter 15 is a little bit shorter, and we'll cover that in the next couple of days. We have our homeworks due on Monday before 10:30 when the exam starts. We have several review sessions to help you get ready for the material. We have the UTFs are going to have a review session on Thursday from 6:30 to 8:30. We're still trying to trying to get a room assignment for that, so I'll post that. And on Friday from 4:30 to 6:20, we'll have an SI super session. All right. We also have a lot of UTF office hours still going on this week, and then of course I'm around as well. All right. So any questions about that? Yeah.
So with the 2 exams, do we get any reference materials that you're going to hand out to us?
Okay, good question. As far as the exams go, what you will get is a list of the spectroscopy tables. Okay? And I have posted under study materials on Canvas on our website the exact copy of the tables that I will provide to you. Okay, so you should go ahead, and they're just from what are in the appendix in the book, but I kind of shrunk them down to fit onto both sides of one page. But make sure to familiarize yourself with that page. You can download it ahead of time so you know what's there. You can bring in a calculator, though. At the testing center and here, if it's, I don't know. At the testing center, they can make sure you have the memory cleared if it's a programmable calculator. So I guess I would ask the same in here. I remember one time when I was teaching at University of Hawaii in the beginning, we taught somebody who had programmed all these chemical reactions into their calculator. And he didn't end up doing well on the exam. So that's not a good strategy. Any other questions? Yes?
Have you posted the link for the molecule of interest yet?
I have posted the link for the molecule of interest. Good question. It is up. Posted it yesterday. So go. Remember, there will be a 5-point extra credit question on the written portion of the exam. So just follow that link, read about the molecule, and the question is typically about something relevant to the chemistry we've been doing. So look at the molecule and ask yourself, what could we ask about that molecule, right? Yeah, question.
Have you so I went to go look at the app, like what's the word I'm looking for? On Connect, the solutions manual.
Yes.
I couldn't find it.
Okay.
And the link wouldn't take me.
Right. So, the publisher, they're still, I don't know why, still trying to figure out some way to give us a number to access that. The link that I posted in the announcement, apparently, it didn't work the way I thought it was going to. But just this morning, under that same announcement, I replied to my own announcement, and I just posted 3 different PDF files. So now you can go in there and you can just download the solution manual for these 3 chapters.
Okay.
And so those are available. Hopefully by the time we're done with this, they'll have the whole thing available for us. Okay?
Thank you.
Yes. Okay, so let's start in. What we want to do today is we want to talk about C13 NMR. Right? That's what we want to talk about. So we're going to go through a little bit about C13 NMR, what it tells us, look at some examples of that, and then we're going to start working some examples. All right? We're going to work a few of the examples that I put in the notes, and then we're going to go to this website called Web Spectra, and we're going to work some examples there. We're not going to work right now in class all of the examples that are in the notes, but what I'll do is I'll go back to my office and I'll fill those in so you can go back and look at those if you want. But this way we'll get more examples and I'll be able to show you this website, and there's a whole bunch more that you can do on your own as well. Okay? All right, before the break, we finished on this slide right here. So this is just a little overview, some basic information about C13 NMR. Remember that for carbon NMR, it's only the C13 isotope which is detectable, that has a nuclear spin that we can detect. And because it only makes up 1.1% of all of the carbon, this is really a much less sensitive technique than proton NMR. The chemical shifts are very wide, going from 0 up to over 200 parts per million. And we usually run the experiment using an approach called proton decoupling, which removes coupling between protons and the carbons to which they are attached. But I'll show you how that works in a second. And the other thing to keep in mind is that the peak heights or the peak areas, the way that this is run, those areas are not proportional to the number of carbons. Okay? There are a couple of things that we can get from this, though, is that usually the quaternary carbons, so the carbons that have no hydrogens attached, are usually small. Okay, so quaternary carbons are small. And the other thing is if we have similar types of carbons, whether they're, say, carbons in benzene rings or carbons that are just CH3 and CH2s, is oftentimes if we have one that's worth 2 carbons and one that's worth 1, they will be roughly 2 to 1 in ratio, but you can't always count on that, all right? So here's two C13 NMR spectra. So they're both of the same molecule. The bottom one is the proton decoupled spectrum, okay? And notice that all of the peaks are singlets. All right? If we look at the structure, this is just butane 2-all. The carbon bearing the oxygen, just like it would be in proton NMR, is the most downfield. All right? And then the other three are more upfield. If we ran a coupled spectrum, so proton coupled, each of the C13 atoms would have protons. If they had protons attached to them, they would be split by those protons in an n+1 way, like we've noticed. So for example, notice here that we see this one as a quartet. That means that there are 3 protons coupling to that carbon. So 3 + 1 gives us 4 peaks. So if you get a quartet, that means that this peak is for a methyl group. So the splitting tells us how many protons are attached directly to the carbon. This is another quartet. This is a triplet. How many protons would be attached to that? 2 protons, right? This would be CH2. Here's a doublet. Means it would be a CH. And sometimes we'll see this. This is actually CdCl3. This is the NMR solvent that we use. So we didn't really talk about that in proton NMR, especially we use solvents that have all of the hydrogens traded out for deuterium. Because otherwise, the solvent is so much more concentrated than our sample is. If the solvent was protonated, the peaks for the solvent would be so huge, they would essentially drown out the rest of the spectrum. Okay? Deuterium is different than what we've seen. Deuterium, instead of this spin 1/2, has a spin of 1, and that ends up splitting the C13 for that solvent into 3 peaks. So we'll oftentimes see this is a common solvent, 77.0 for deuterated chloroform. Okay? So sometimes what you'll see is if you have a decoupled spectrum, you could possibly see things like this: a D, a T, a Q, and a Q. So what these mean is what the peak would be if it was coupled. All right? So if you see a Q, you got a single peak, but it says Q, that means it would be a quartet. It means it has 3 hydrogens attached. Okay? The chemical shifts in C13 NMR generally mirror what we would see in proton NMR. Okay? Except there's a few things we can see that we can't see in proton NMR. So for example, at the most upfield direction, we see protons that are just alkyl types of carbons. Or not protons, carbons that are alkyl, right? So just alkyl groups says between 5 and 45 parts per million, okay? And like in proton NMR, the more substituted they are, the more they tend to be at the downfield range of that. And in fact, if they have a lot of substitution next door, it can cause them to move downfield as well. In the next region, just like in proton, and well, one of the next regions in proton NMR is where we have more electronegative atoms attached to the carbon. So same thing here. We could have halogens, oxygen, nitrogen, and this chemical shift difference, like we saw before, is just based upon electronegativity. The more electronegative the group, the more it pulls electron density away from the carbon, the more it de-shields it and moves it downfield. Okay? Alkynes are next. They have a pretty wide range. And then we get into the sp2 hybridized carbons. All of the sp2 hybridized carbons are at the downfield half of the spectrum. So they say somewhere between 100 and 140 for just double bond carbons. And these are not really exclusive. You know, depending on the molecule, we could expand these gaps, ranges a little bit. 120 to maybe 150 to maybe 160 for carbons in benzene rings. We would be at the farthest downfield end of that if we, say, attached an oxygen directly to it. Right? We'd have an electronegative group, it would de-shield that as well. Now, a type of group we could not see in proton NMR were the carbonyl functional groups. Okay, so the carbon-oxygen double bonds, and these are very apparent in C13 NMR. They say 160 to 210, but we can actually split those into two groups. Okay, so let's split these in half. Let's say 160 to 180 will be carbonyl groups that have some, say, some electronegative atom attached. This Z group could be an oxygen or a nitrogen, or the more common. So esters, carboxylic acids, amides, those kind of functional groups will be between probably 165 to 180. If we go 190 up to maybe 220, this is going to be either aldehydes or ketones. Okay? So those will be able to see better. So this is Appendix F. That's the one that I'm giving to you for the exam. All right, so let's just look at a few examples. I think the top one is the one that I showed you already. Out of this, we can see the one thing up in this upper range. This is just going to be the alkyl portion. And it's sometimes going to be a little hard for us to specifically assign which ones are which there. Okay, because it depends on substitution and what's adjacent and things like that. But clearly, we have this carbon at almost 70 parts per million. This is going to be the carbon that's attached to the oxygen. So that's the one we can really pick out clearly. In the one below, likewise, carbon bound to oxygen, and then probably, then B and then C, we're just going, CH2, CH3. Okay, so we can oftentimes count the number of carbons, but like in proton NMR and like we talked about before, if there's symmetry, then we'll see less than the maximum number of carbon signatures. Like this one. Okay, so we see 3 peaks. This one all the way up at 192 is going to be for the ketone. Okay, so that's clearly in the carbonyl range. And then we have a CH2 and CH3. We only have 3 peaks because there's a plane of symmetry right through the carbonyl. So the 2 ethyl groups are equivalent to one another. But notice, the quaternary one is small. We can't really integrate that one to these other 2 to determine our symmetry. Okay, the one below is for an ester. And so notice that the carbonyl here is more at like 170. So the ester is 170, the ketone is almost 200. Then, because we have an ester, we have this methyl group, we have one of the other carbons that's bound to oxygen. And so again, this is at 150, so this is the carbon bound to oxygen. This is the carbon, the CH3 that's next to the carbonyl. It turns out being next to a carbonyl doesn't make a big difference in the C13 NMR. Okay? One thing that you can get a lot of in C13 is it's very good at determining symmetry. So for example, here are 3 different spectra. They're all for isomers of dibromobenzene. Okay, so let's draw out the 3 possible isomers of dibromobenzene. Right, so if we have a benzene ring, we could have the 2 bromines on adjacent carbons. We could have those bromines in a 1,3 type arrangement, or we could have these bromines in a 1,4 arrangement. Right? So these are the 3 possible constitutional isomers of dibromobenzene. So let's think about, for each of these molecules, how many carbon signals we would expect. So the number of signals. So what about this top one? 3, right? Because there's a plane of symmetry right here. And so, you know, these 2 would be the same, these 2 would be the same, and these 2 would be the same, because they're reflected across this plane of symmetry. What about the second one down? 4, right? So this plane of symmetry goes right through these carbons and hydrogens. And what about the bottom one? Just 2, because there's a plane of symmetry going through the bromines this way. There's also a plane of symmetry going this way. So we have all of the protonated carbons as one signal, and the carbons bearing the bromines as the other signal. All right? So, just based upon the number of peaks we see in the spectrum, we can assign which spectrum goes to which compound. So the top spectrum, which compound is that going to go to? The bottom one, right? Because it has only 2 signals. You see the small one for the quaternary carbons bearing the bromine, the big one for those 4 carbons that have protons on them. What about the middle spectrum? It's going to be for the top one, we see 3 peaks, and the bottom one has 4 peaks. Okay? So we didn't need to know anything about chemical shift on this problem. All we needed to know is about symmetry and how many peaks we would observe.
Like a mixture of the different isomers.
Well, if we have mixtures, then things get much more complicated, obviously, right? And so if they were equal concentrations, then we'd have a hard time telling which peaks went with which molecule, right? If they were in different amounts, if we had, well, a mixture of 2 and we had some that were more concentrated than others, maybe we'd see one set of big peaks and one set of small peaks, and maybe we could analyze it that way. But once it gets to be a mixture, it's very difficult to deal with. Yeah. Okay, so let's look at this one. We have proton NMR and we have C13 NMR, and we have a formula up on top. Okay, so there's our molecular formula. So let's start out by figuring the number of unsaturations. How many unsaturations do we have? Just one. So how do we deal with the chlorine when we're calculating unsaturations? We treat it just like a hydrogen, right? Because it has the same bonding characteristics. All right, so which one do you want to look at first? So just somebody pick something out that tells them something. Right, look at this one right here. Looks like a carbonyl. It's at about 170. So what does that tell us about that carbonyl? It's probably, if we have two oxygens in the structure, it's probably going to be, it could be either an ester or it could be a carboxylic acid. All right? If we look up at the proton NMR, could we tell the difference between an ester and a carboxylic acid?
Well, I mean, with a carboxylic acid, usually a singlet.
Right, for the carboxylic acid, we should have this OH of the carboxylic acid, which would be out at a very downfield position between 10 and 12 parts per million. Okay, so, but we can probably narrow this down in this structure to something like this. Okay? Then, to also determine between those, we could ask ourselves, do we have a carbon that's attached to oxygen? Where would we find that? Where did we see it in those other couple of spectra? Like in the 60 to 80 range or something. So this carbon right here is probably a carbon bound to oxygen. Okay, what about in the proton NMR? Does it look like we have any protons on carbons that could be attached to oxygen? The spectrum looks more complicated than it really is since it has all those expanded parts. So out here in the 3.5 to 4 range, this is out where we would have carbon bound to some electronegative, more electronegative group. Okay, we have oxygens and we have a chlorine to put in the molecule as well. Okay? So what else can we pick out here? Let's look at this signal right here for 2 H's. What kind of a splitting pattern does it look like? A quartet. What does that tell us? That's a methyl next to it. All right? So, do we have a methyl? Yeah, over here, right? So these two have to go together. Okay, so that gives us an ethyl group. And that ethyl group has to be attached to something to push the CH2 so far downfield. So it's probably the oxygen. If it was the chlorine, then ethane would be a complete structure. It couldn't be part of this structure. Right? So this has got to have an oxygen right here. Okay, then what else do we have left? So we've taken care of this signal and this signal. We have these two left over. So the chlorine's got to be attached to one of those. But we have, what are the two splitting patterns for those two carbons? They're both triplets. So that means that it has to be a CH2 attached to a CH2. Right? Because the CH2 will split the other protons into a triplet in the same way back the other way. So we have, let's put together this molecule then. We have our ester. We decided that the ethyl group has to be attached to the oxygen. Okay? We have a CH2-CH2 group then that has to be over here. And what's on the end? The chlorine. Okay? So oftentimes what we're going to have is we're going to have several pieces that we should be able to identify. We've got the ethyl group, we have this CH2 group, and we have to link those together somehow. So in this case, we link them together based upon having the ester, right? And then knowing that, that we have to put the chlorine somewhere. Okay? All right, so this is where I'm going to stop here, and I'm going to have to switch over to the computer, and I don't have Panopto or something, and so we're just going to work some problems, but I'm not going to be able to record them. You'll be able to go back. I'll show you how to use the site, and the answer keys are there, or at least the structures are there, and you can practice those as much as you want. Hey everyone, I'm following up after class, just as promised. I'm going to work my way through the rest of these slides to give you a few more examples. So in this first problem, we have a formula of C8H9Br, so that is the same as C8H10, so we will take 8, this is our unsaturations, equals 8 minus 10 divided by 2 plus 1 equals 8 minus 5 is 3 plus 1 equals 4. So remember we said that if we have 4 or greater unsaturations, we are likely to have a benzene ring. And here are our carbons for the benzene ring. So we see that we have some symmetry here. We only see 4 signals out of 6 possible carbons. So this gives us some information about our substitution pattern. Also what we see is we have 2 signals, this one and this one, that are very short, and these are likely to be quaternary carbons. So we have several possibilities. We have 2 different groups, X and Y, could be like this. We could have X and Y like this. Or we could have X and Y like this. So the example on the left, if those groups, the X and Y, are different from one another, we should see 6 signals. All would be different. The one on the right, likewise 6 signals. That's the one in the middle. The one on the right, we should see 1, 2, 3, 4. 4 signals. So we probably have this type of 1-4 substitution pattern. After we have our benzene, we see that we have 2 carbons up here. Could be, methyl, ethyl, something like that. And we have to place a bromine somewhere. So we have 1-4. If we put a bromine on one side, we're left with an ethyl group on the other side. Is there any other possibilities? Well, in fact, there is one more possibility. We could put a CH3 group on one and a CH2 with a bromine on it on the other side. Okay, so based upon this data, either of these are pretty good choices. Of course, if we had a proton NMR to go along with this, we could easily tell the difference between these two. In the proton NMR, we would see this ethyl group, a quartet, and a triplet. And if we had the proton NMR of this one, we'd have the methyl and the methylene, the CH2 group, both as singlets. So that would be easy. All right, one more. C4H10O. We have 0 unsaturations. Okay, we have to account for 4 carbons, though, with only 3 signals, because this one is trimethylsilane. Remember, that's our standard. So we have to account for this. We notice that we have only 1 carbon that is likely bound to the oxygen. So this suggests that this molecule would be an alcohol rather than an ether. So we have an alcohol like this, and we only need 3 signals. Let's look at some different possibilities. We have 4 carbons. We could have butanol. We could have this one, or we could have this one. Okay, so let's think again about how many signals we should get for each one of these. What about the top one? Okay, we should get 4 signals up here. We should get 4 signals here. And what about the bottom one? Only 1, 2, and both methyl groups are going to be equivalent, so this would only give 3 signals, and so this is the correct structure. Alright, what about this structure? C6H12O. This gives us 1 site of unsaturation. Alright, again we have a carbon bound to oxygen, and then we have some that have just more like alkyl groups. Alright, we don't know if they're CH2s, but since this is just carbon bound to oxygen and there are no carbonyls, we have no carbon-carbon double bonds, so it means that we either have to have an alcohol or an ether, right? But the molecule can't be fully symmetrical because then we would have 3 signals instead of 4. Alright, so we need some symmetry. And we need probably a ring because we don't have any double bonds. Okay, so we could try some different rings. We try a 6-membered ring and add an OH. What about that? Yes, that would work, right? Because we'd have 1 carbon, the carbon bound to oxygen, 2, 3, 4. This is the same as 2, same as 3. Okay, anything else? Is there any other possibilities? Well, let's look at what if we went to a 5-membered ring and we put a CH2 and an OH. Then we would have 1, 2, 3, 4. 3 and 4. So maybe that's even possible. Alright, so we might have a couple of possibilities. I think that cyclohexanol over here is actually the right structure, but again, it's hard to 100% be sure in this case. Alright, so now we're given a C13 spectrum and the proton NMR spectrum. Okay, we have a formula, C7H8O. Let's see, unsaturations equals 7 minus 8 halves, so that's 7 minus 4 equals 3, plus 1 equals 4. We likely have a benzene ring here, and because it's only C7, we're only left with CH3 left over, because we have
5 carbons around this ring. We need to put something in the middle. We've got the oxygen. So methoxybenzene. Alright, so if we look around here, this goes to that carbon. Okay, the interesting carbon out here, this one all the way out to 160, it's almost to where a carbonyl would be. But that is the carbon on the benzene ring that bears the oxygen. The short one here is going to go to the end, because those, even though we can't integrate them, those are similar kinds of carbons, and we see it's kind of a 2-to-1 ratio. And the other two, turns out that the most upfield one is going to be next to the oxygen, downfield one is going to be further down. Alright, so we can tell the one next to the oxygen is the most upfield based upon some resonance. So if we draw this methoxy group, because the oxygen has non-bonding electrons on it, it can donate its electrons through resonance into the benzene ring. So this gives us a resonance form that looks like this. This. And in fact, we could continue resonance all the way around. We'll learn more about this in the chapter on benzene, but we have a partial negative on both sides next to the oxygen. That negative charge causes shielding. Alright, moves it upfield. So that's how we could assign those. So we didn't even really need the carbon, the C13 NMR spectrum, or the proton NMR spectrum, I guess. We have 5 H's here. That tells us that we have this mono-substituted benzene ring. We have the OCH3. Is it like 3.7 or something? That fits good. So all of this fits that structure. Alright, so here's our last one. C8H10O. So what do we have? Unsaturations equals 8 minus 10 halves minus 5 is 3 plus 1 equals 4. So again, look at this. We've got 4 signals here in a benzene ring. And we have only one way up here at less than 20. Okay. We don't really know what that is, though, at this point. If we look at the proton NMR, we see 2 signals. Here's the blow-up of aromatics, and these look like they're in roughly a 2-to-1 ratio. 2-to-1. Then we see 1 over here is just kind of this little nondescript peak. And this is a little tricky, but if we cut this thing in half, I'm thinking that this is probably 3 and 3, so this is worth 6. So this would have to be 2 times CH3. Alright, so that's 6. We've got 3 over there. 6, 9, 10. Okay? So let's do our benzene ring. Okay, it's 2-to-1 in the benzene, and you can tell that they couple to each other. So what that means is that those protons need to be on adjacent carbons, and they both have to be coupling to this one that's worth only 1. Alright, here I'm going to move this away from the edge so I have more room to draw. So I'm going to put one H in the middle and an H on either side. Okay, the one in the middle goes to this. It's only worth 1. And the 2 on the outside go over here. Okay, we're going to have substituents on all 3 of the other carbons. And so the 2 outside ones only couple to the one in the middle. The one in the middle couples to both of those outside protons, so it makes it into a triplet, as long as it's symmetrical. Okay, we have 2 methyl groups all under one signal. And so this has to be symmetrical, so I'm going to put a methyl group on each side here to keep it symmetrical. So then what do we have left over? This is C8H9. C8H9, we have an OH left to go. OH. This OH is here. So OH proton signal is often broad and has a wide chemical shift range because it can hydrogen bond. Alright, so let's look at this upper one. Let's just draw it out again and let's see if we can pick out some of these carbons, a couple of them at least. OH. Okay, so both of the methyl groups have to be under this carbon over here. So it's symmetrical. They both give one single signal. Now the main one that we can see here is this most downfield one, is the one bearing the oxygen. Probably the other one here, because this is in a 2-to-1 ratio, is that these 2 carbons probably go to this biggest one. And then it's a little unclear which ones go to the other ones. Okay? So this is what we might come up with for these structures. So the more practice you can do here, the better you're going to get, the faster you're going to get. So I'll post some specific problems off of that website, the Web Spectra site that we looked at today, that you can work on.